Hello everyone, welcome to our new video in our finance course. Now today we will talk about chapter 5, which is about time value of money. So let's start with few basic concepts that we will be using throughout this chapter. The first one is the so-called future value. This is the amount which a cash flow will grow over a given period of time when we compound our cash flow with a given interest rate. And then we have the so-called present value. And this is in some sense the opposite direction. We are going backward in time. In future value, we are calculating the future value in time. But we can know the value that we will receive in a future date, but we want to calculate the value today. Okay, so that gives us the present value when we find the value today for a given cash flow. And compounding is the arithmetic process of determining the final value of a cash flow or a series of cash flows when compound interest is applied. In other words, just like when you deposit your money in a deposit account in the bank, you start, let's say, with $1,000, and then next year it will grow to 1,005, let's say, with 5% interest rate, and then you will reinvest actually this $105 for another 1 year, and it will compound again with the given interest rate. So this is what we call as the compounding, and we will have some basic examples. So we will use the notation here when we write PV that will represent the present value or the beginning amount. And let's say in our example, suppose the present value is $100 and the future value, we can denote this with FVN. So here N basically refers to the N number of periods. So PV is the value now, as we just defined, as present value, and FVN is the value at the end of these n periods in the future, after we have considered the interest added in the account. So here is a more detailed diagram or demonstration. So for example, as we said, you might have 5% interest rate, and your money initially, if it is $100, that's going to grow 5%, and you will get 5%, which equals to $5. So this 5% is $5 of interest during the first year. So your investment grows to 105. And then suppose you reinvest, you continue to reinvest, and this time your interest will be calculated based on the $105 here. So as you see, the interest you earn grows over time as time goes on, because your as a result of reinvestment, your actually investment is growing over time, and therefore the interest that you receive is also growing. So this is called as compounding, and interest earned on interest is called compound interest here. As you see, we have earned this $5, but now we have one more interest applying, okay, as a compound interest. So this process continues, and because the beginning balance is higher at each time, for example, here the beginning balance becomes $110.25. So the next time you will get the interest rate as the difference of these two numbers. Okay, as you see, the interest you are earning is growing. So the total interest earned, for example, at the end of these 3 years is given as 15.76. This is reflected in the final balance that we see here. So depending on how many years this investment continues, we can calculate this compounded return, basically, what we compounded also in the interest. So we have a basic equation that describes this basically growth of the future value given the present value of your investment. If you started with $100, then given an interest rate denoted by I, so this is the interest rate, and you are assuming that we reinvest this for n number of periods, then our compounded amount will become present value times 1 plus the interest rate to the power n. As you see in our example, just in the previous slide, the future value at the end of 3 years is calculated by 100 times the 1 plus 5 percentage. This is the interest rate is 0.05. So basically this is compounding here, and 3 periods, 3 years in this case, that gives us the future value at the end of 3 years. Okay, so we can now visualize this in a cash flow where you might have some investment, and the initial investment or the present value is, let's say, is $100. So basically we are spending some cash, and if in a step-by-step approach, we already have seen the formula to calculate the future value, and the future value at the end of 3 years of an initial investment of $100 grows to 115.76. So we can do these calculations also in Excel. There are particular functions for calculating the future value, and that is given by the function fv in Excel, where you need to input the interest rate, the number of periods, the payments, the present value, and the type here. So for example, in this particular problem, we have the 5% interest rate for 3 years. This is the interest rate per year, and then we are receiving 0 payments in between until the end of these 3 years, and we just have $100 of, we put this as a minus sign if there's a cash outflow, and that gives us $115.76. So the calculation of a present value is the reverse of finding a future value. So in our formula that we have already seen, it's not difficult to actually write the formula for the present value given the future value of an investment or a cash flow. So basically, if you are given the future value instead of the present value, you can calculate the corresponding present value from this investment. Furthermore, we have the so-called opportunity cost, which is quite commonly used in economics. That refers to the rate of return you could earn on an alternative investment of similar risk. Again, this would be, for example, like a benchmark for you if you are considering whether to invest or not in a project. Then you can compare the opportunity cost, right? You can, for example, you want to start a new business, let's say, and you should basically compare the potential rate of return from this investment, at least with the deposit rate from the bank. That you will be earning if you put this capital in a bank account. And there are also different types of opportunity costs you can consider. Okay, and we have the so-called discounting. That's the process of finding the present value of a cash flow or a series of cash flows. Discounting is the reverse of compounding. So for example, if we want to find the interest rate, then we would need to know what's the future value and what's the present value. And then we can solve this equation for the interest rate, just treating the interest rate as the unknown variable here. So this might be useful when we know how much we are going to get at the end of this investment. So we know what's the future value, how much money our investment will worth, and we also know how much we need to invest at the beginning, the present value. And then in this type of scenario, you would be interested to calculate what's the interest rate that you are actually earning from this investment for 10 years, let's say. As I said, this is just the way we can think about this. And alternatively, you might also be knowing the other parameters. For example, the only unknown parameter might be the number of years. And we might also know the interest rate. That should be, of course, known. But we don't know how many years do we need to wait to actually reach this future value. So you can think about this equation. For example, you might have a target amount, future value, that you want to reach. And you have, let's say, $100. And given the interest rates are, let's say, 5% per year, you might ask the question, how long is it going to take, let's say, for my investment to double? So I invest $100 and I want to know how long it will take for $100 investment to become, let's say, $200. If you are curious about this type of a question, then you can use the formula here. Of course, here this interest rate should be already known, right? Otherwise, we cannot solve for n. We have also the so-called annuity, and annuity can be the so-called ordinary annuity, where we have, let's say, 3 years time period, and each time the payments are given as $100 at the end of each year. And also the annuity due, that would be given as the payments starting from time 0. Okay, and that is done at the beginning of each time year, each year, sorry. So we can calculate the future value of an ordinary annuity. In the ordinary annuity, we are basically having these $100 payments at the end of each year. So you can calculate the future value, because this $100 is received, remember that's at the end of 1 year, and here we are interested in the future value at time, at year n. Okay, so if we call this as year n, so you have n minus 1, n minus 2, n minus 3. So you can go and n minus 3. So basically, if we are receiving this $100 here, and at the end of the last time period here, let's say, okay? So in order to calculate the future value at time n, this $100 payment, this will be compounded with 1.05 squared, because we have two more years to come to this final time n. So this one is multiplied with 1.05 squared, so this is compounded twice. And what about the payment here? This is $100 of payment, and it is compounded one time to come to the future value at time n. And basically, the last payment here is at the same year n, so we don't need to have any compounding, so this is just equal to 1. I mean, that's this is already given at the same future date that we are trying to calculate here. So altogether, this gives us the future value of this annuity where we receive $100 at the end of each year. So this type of annuity calculation can be generalized and can be represented in a formula that is more compact and easier to use every time we need to calculate a future value. So in this case, the formula, remember, we have these payments that are made at the end of each year, and then we are calculating the future value of these payments. But we can notice that the payments are fixed, so we can take this out first of all, and then write the sum of these geometric series using the formula from geometric series, okay? Because every time we have 1 plus the interest rate, this is the interest rate, and this is this expression is going over with the geometric terms here in this summation. So it can be summarized within this formula. This is actually from calculus knowledge about the geometric series. So you can refer to any calculus book to basically check this formula. But at the end, this formula can be directly used for our questions. And then for an ordinary annuity, as we have, we can calculate now the present value. Now for the present value, remember in the previous slide, we calculated the future value, but now we can calculate the present value. In the present value calculation, remember each payment, for example, you might have n number of years again, and you receive, let's say, $100 at the end of 1 year. So this $100 will be discounted back to the current time 0. So this is time 0. And we are interested in calculating the present value at this current time, okay? And then this can be year 1, and then you have year 2, and so on. I mean, depending on how many years do you have in this annuity, you can continue this calculation. But this $100 will be divided by 1 plus the interest rate to discount it to time 0. So the second payment, you have another $100 payment, and you will need to discount that by taking back to time 0. So you need to divide by the discount factor squared, okay? This is 1 plus the interest rate squared. And similarly, you just write all the other terms for taking the present value of this guy, this payment of $100. Again, you need to take it to time 0, where the discount will be 1 plus interest rate to the power n. And again, this is from the geometric series formula from calculus. We can write, because these payments are fixed, so we can write this in this compact form. And if we know what's the interest rate, then we can easily calculate the present value of an n-year annuity, okay? And suppose this annuity, if it is for n equals to 3, and if the interest rate is 0.055%, then the present value of this annuity for 3 years equals to 272.32. Okay, so let's check a question, and then we will stop our video. So in this example question, you have you suppose that you just won the Florida lottery, And to receive your winnings, you must select one of the two following choices. So these two choices, first, you can receive 1 million a year at the end of each of the next 30 years, okay? Or the second alternative you can choose, you can receive one-time payment of 15 million today, okay? And assuming that the current interest rate is 6%, the question is which option is most valuable, okay? I mean, we have just seen the present value and future value. So based on this argument, you can analyze which option gives us a higher present value as of today, because we know that the interest rate is 6%. So we will choose whichever option gives us the largest present value. Okay, so we need to calculate the present value for both cases. And as we said, the second option is directly immediate payment of $15 million. So the present value is just 15 millions, right? Because it's the immediate payment. So what about the other alternative, which was $1 million for 30-year ordinary annuity, okay? And basically, if we have this, just imagine, I mean, if you multiply actually 1 million times 30, that gives a bigger amount, okay? But we need to calculate the present value, of course. I mean, we cannot just say 1 million times 30, it is $30 million. No, each 1 million that you will receive in the future, the present value is actually lower and lower as you need to wait a longer time, okay? So you can apply our formula. What did we said? We have 1 million as the fixed payments each year for the annuity, and we have a 6% interest rate. So this is 1 plus 0.06 for 30 years, and then we divide by the interest rate. So if we do this calculation, you can use a calculator. That gives us 13.76, something around 13 million, okay, $13.7 million, which is smaller than this $15 million in terms of present value. So choosing the immediate payment of $15 is more valuable based on these assumptions that, you know, the given interest rates. So we will stop here with this example, and thank you for watching.